Today, network expert Mike Motta is going to be discussing how to troubleshoot TCP segment flow problems. For us to provide a cleanly recorded copy of this web session afterwards, all lines have been muted, so that way we don't have any disruptions during the broadcast. Please feel free to ask questions. We would encourage you to use the question function. Type in and send in your questions, which will be answered through the program. We'll also have time at the end specifically to handle questions as well. So, and that engagement, I think, is really, really valuable, certainly what we've noticed throughout the week. So please keep questions going through there. And without further ado, I will turn it over to Mike Motta.
All right. Thank you, Steve. Well, hey, good morning to everyone out there. Thank you for attending this Shark Week webinar series sponsored by Network Instruments. So my name is Mike Motta. Started my company, M&EX, about 1998, and I've been using analyzers since 1979. If you've been around the industry for a while, you know that TCP/IP started as a part of the Department of Defense in 1974. And so I feel very blessed to have gotten to grow up with TCP/IP over the years. Again, I founded my company in 1998, and that is mnex.biz. You're welcome to go to our website. As a matter of fact, I would encourage you to go to our website. As you get old like me, I'm 38 in hex, so as you get old like me, we tend to end up with this thing called CRS disease, which is can't remember stuff. And I have put together with a friend of mine this frame header information that you can easily download from our site. It's basically an Excel spreadsheet that has a lot of the packet information, packet headers, IP headers, TCP headers, UDP header, lots of good information, all in a beautiful Excel spreadsheet. And so you can download that spreadsheet from our site just by clicking on that link there. Frame header information, and you can pull that off of our site and have that available to you in your iPhone, iPad, wherever, so you don't have to carry any big old thick books around. Secondly, I would encourage you to sign up for one of our classes, our next upcoming class in February for Wireshark. We do have some self-study classes. If you missed some of our earlier seminars here this week, one of the things we showed you was how to add columns and add profiles into your Wireshark. So there's a little link to that. If you have missed or need to know how to do that, that's right there. So we're probably not going to go back over all the stuff we've done the past couple days. So welcome to all the newbies, and if you've been on the call the last couple days, thank you for attending. Again, come on down to a class, Kansas City, our next one, February 9th through the 12th, or, hey, you know, I can come to you if you have enough people to train. So frames don't lie. That is my favorite adage. There is no new way to get data from my PC or my laptop, my whatever, iPad, iPhone. It's got to come across the network in frames to get to the server and the application that rides on the server that we want to communicate with. So if we can capture those frames, frames don't lie. We can prove where does the time lie, where is the latency. So in TCP, there's a couple things. There's the virtual circuit or socket that's getting set up when the client establishes the session, sends a sync request to the well-known server listening server ports. So for instance, port 80, we all use port 80 for the web. So I send my sync request to port 80. The server hopefully will reply back with a sync ACK to the port that I started with, the ephemeral, short-lived port that the client starts with. The client then will ACK, and there's our three-way handshake, TCP three-way handshake, to establish that call or that socket network circuit across the pair. And we can time that and use that information now for giving us how fast or slow is the network. And I always think about why would we have started this process in the first place is typically someone complains the network is slow. And that's music to my ears. When somebody says that, I think, okay, here we go. We're going frame hunting to figure out what's wrong, where's the latency in the process of client-server communications. And again, the majority of well-known server listening ports are defined by IANA. You can go out to IANA.org and get the list of ports. Now, I would encourage you not to print the list. It's a pretty long list. You might generate a lot of paper. So just have that bookmarked if you need to know all the different ports. But this is the beginning of the process. So client sends the sync request. And in that sync request, what we're establishing is the initial sequence number that the client is going to use for its half of the conversation. So we'll just say sequence number equals X, and this is the only time that we're going to start adding 1 to our sequence numbers, and this is how we synchronize our sequence numbers. So the client sends, in its sync request, sequence number. It's going to tell the server its receive window size. It's going to tell it the different options that it wants to support, like max segment size, 1460. For those of you math gurus and you know your protocol headers, 1460 of application data plus 54 bytes of protocol overhead minimum, 14 DLC, 20 IP, 20 TCP, 54. That's 1514 plus a 4-byte CRC, and we've met our maximum frame size for Ethernet. And if you don't know that, well, come on down to class. We'll teach you. So there can be other options that are negotiated as well. So sequence number X plus 1 is the server's ACK number. So we see on the server side, if it receives the sync request from the client, it takes the sequence number from the client. Plus 1 is the appropriate ACK, saying, okay, I agree, and it's going to synchronize, hopefully. It could also send a reset at this point, which would basically say it's not willing to synchronize. But in this case, it is, so it's going to tell the client its initial sequence number, its receive window size, and again, all the different options that it can support and wants to support. And then the client will send an ACK with the server's sequence number plus 1, and there's our three-way handshake. We have all agreed to establish that session. And at that point in time, let me jump out here into my DOS prompt. At that point in time, the server and client both will put in their netstat table that socket circuit session based on IP address and port pairs that are in use for that conversation process. And so you can see here that that socket is established. Some are listening, so they're waiting for the sync to be received from the client. So basically that app is there and running and willing to accept the connection request. And we'll talk about what those can be, what are the different options. But right now at this point, once this process has completed, then we have established our initial TCP three-way handshake, and from this time on, we will increment sequence numbers based on the amount of data payload that we're going to send in that particular packet. So we talked about there's options that get negotiated when the client and server both start that session socket circuit. So there's some RFCs. Those of you that love to read RFCs, I would encourage you, in your spare time, RFC 791 is what has started the IP protocol. 792 is sort of the invisible protocols, ICMP, etc. And 793 is the original RFC for TCP. So I've kind of given you some of the RFCs. I would encourage you to go at your leisure to read or at least peruse those RFCs and understand how the process is going to work. Obviously, it goes without saying, I cannot teach you everything there is to know about TCP IP in 1 hour. And I know you're going, darn it, but that's the way life is. It's going to take you a little while. So start with the RFC 793. This is where we negotiate maximum segment size. Some new things have been added over the years: window scaling, scale factors, so we can increase the receive window from 16 bits, which was the original 2-byte in the TCP header, receive window 65,535. So that's kind of a small window by today's standards. So there are mechanisms to increase that with the window scaling and scale factor. SACs, if we're going to increase our window size, then we need to provide for selective acknowledgments, which are a more efficient way to retransmit data in TCP. And we can also negotiate timestamps so that we can use that for round-trip measurement time. And there's always new things, experimental options being added, like multipath TCP. So there's things all the time being proposed. So, kind of keep up on your RFCs. We're into the RFC 6000s today, so there's many things happening in the world. But these are the main things that we're going to talk about from the perspective of TCP and how the process flows. So again, those options, the NOP is basically to ensure the no-op. The TCP header must end on a 32-bit boundary. So that's the whole purpose of that, is to ensure that we're using multiples of 4 bytes or 32 bits. Our max segment size, again, I just kind of told you that 1460 is the most efficient when we add all the protocol overhead. So if I send down from the application 1,460 bytes, TCP adds 20 bytes, minimum 1480. Hand that down to IP adds 20 bytes, 1,500. There's your MTU. Then we hand that down to the NIC, and it adds the 14-byte DLC header and 4-byte CRC, and we're at 1518 max frame size for 10/100 Ethernet. The window scaling option, we talked about, we can increase that. There was a saying made years ago, you never need more than 64K of RAM. Well, yeah, we've kind of gone beyond that. So the same. When TCP was architected in the 70s, a 64K window was a very big window, but that is no longer the case. So today, with jumbo frames for gigabit Ethernet, we can, 9,000 byte frames, all of a sudden that 64K window becomes relatively small. So with this option, we can now increase the window size to a gigabyte. And you can kind of figure out, if we got gigabyte windows in play, you can't have that many sessions on your server unless you got lots and lots of RAM. Selective ACKs, again, selective ACKs are a more efficient way to do retransmissions in TCP. The old days, if we didn't use selective ACK, if there was a packet dropped or a packet lost for whatever reason, we would have to retransmit from that point through the full window. And today we can tell the other side, hey, I'm just missing, 1 segment or 2 segments out of the 8 segments block that was transferred. Timestamp option, again, we talked about, you can use that for measuring round trips. So those options all get negotiated in the sync request. So what does TCP offer? This is always the hard part, and it's math. If you think about all that TCP does to guarantee that what I sent you is what you received, is it's basically done with math. So in that sync request, we set up our initial sequence number. And from that moment on, again, in the sync, you're going to add 1 for the ACK. And then once both sides have agreed and we've set up that socket, from that point on, the sequence numbers will only get incremented by the amount of payload, TCP length, that is being sent, sync application data at that point. So that sequence number plus the payload is the ACK that I expect, or it may be the next sequence number. If you've told me, for instance, you're the client and you say, hey, I want whatever, the customer database, well, the server doesn't know how big the customer database is, so it sends that request up to the application, and the application starts sending data. Well, that customer database may be, 10 meg. We can't send that in one packet, so we got to start breaking that up into pieces that we can move across the network. So it's It's going to be sequence number plus length is the next sequence number based on what you've told the server was your receive window size. And that receive window is how we determine the flow control process for that conversation. So there's a lot of stuff going on in TCP to guarantee all this works and makes it from point A to point B. And then, you know, man, our lovely routers and firewalls and switches and things in the middle can drop packets for us. So TCP guarantees that if we don't get our acknowledgement for the data that we sent within a certain amount of time, that TCP will retransmit that data. So based on sequence number plus length, the appropriate ACK. So I sent that data to you, started sending that data to you. I start my retransmission timer, and if my timer expires and I have not received the acknowledgement from you, I will retransmit that segment. And we can presume then retransmissions are typically caused by lost frames, CRC error frames, you know, something in the network that is potentially causing us a problem. We talked about flow control, that, you know, when we establish our initial session, the client tells the server its receive window, and the server in its sync ACK tells the client its receive window, and that's our sliding window that we use now to manage flow control. So as data traverses the network, the server sends data to the client and tries to fill the client's window. You know, if it does, if the server fills the client's window, at that point, the client says, I can't receive any more data, so it sends a window 0 saying, don't send me any more data. I know I asked for the customer database, but here's all I can receive. You've sent me that. I've handed it up to the application. Now I have to wait for the application to give me those resources back to the TCP stack, and then it can reopen the window. So you'll see in your traces, TCP window updates, things like that, notifying the other side that, you know, I've closed the window has shrank to 0, and now I have the resources back to continue the flow of data across this socket. And again, the positive acknowledgement with retransmission process works with that window as well. So if I send a block of data, multiple segments across the network, I expect an ACK for all those segments, and off we go. Okay, I already got a question. Here we go. Cisco ASA can randomize sequence numbers. I agree, it can. And how will that work if the client and server is expecting a sequence number plus length? Well, it works exactly the same. So just because you're randomizing a sequence number, TCP randomizes the sequence number. Everybody is supposed to. So if the ASA, think about the firewall is terminating those TCP sessions, I'm sending the sync request. I'm presuming that, you know, you're doing this across a VPN client, and the ASA is terminating the VPN end of this. So if I'm sending the sync request, the ASA is terminating that. It's technically sending the sync ACK back. I presume, since I don't know your architecture, I'm just going to, you know, make some assumptions, and we all know what that means. So here we go. If the ASA terminates the session, it's going to send the sync ACK back. Client's going to ACK. So where are you capturing from? Are you capturing, you know, in front of at the client side with Wireshark, or are you capturing on the behind side? So now the ASA has got to keep a table. It's going to start a connection from the firewall to the whatever web server. Another sync request goes out then from the ASA to your web server, and it sends a sync ACK back. So if you're capturing on that side, you know, yes, different sequence numbers. It's a different conversation. However, you know, the same process works on either side, client side or server side. And yes, sequence number plus length equals ACK works on both sides. So good question. But again, since I didn't architect and don't know your network real well, I'm just sort of making generalizations. So this same process for TCP happens on multiple conversations, connections, sockets, circuits. Again, think about HTTP, for instance. Why we don't use HTTP 1.0 any longer. It only sets up one session socket circuit between the client and the server. So if we have packet loss, that really can affect the loading of a web page. So with HTTP 1.1, we can have multiple session socket circuits. So if we're having packet loss on one socket, then things can still be happening on the other session socket to load pieces of the web page. And 2.0, HTTP 2.0, again, even more than 2 socket circuit sessions can be in play. So all of these things, all of these sessions, socket circuits have the same process happening with them. So I would encourage you in your troubleshooting process, always filter to one socket circuit session, because all of these sequence numbers and ACK numbers, they're big numbers. They're 32-bit numbers. They all start to look the same, and we're going to look at that here in just a second, and you'll see what I'm talking about. And then finally, each TCP header has a checksum, and if you missed the whole checksum offloading things that we've done the other days where we spent some time on why you don't want the NIC to do the checksumming, well, go back and listen to those. We're not going to go back through that today. We did already discuss that. So every TCP header has to calculate the checksum based on the payload that it is carrying, adding the TCP header, and then checksumming that. And so we want to validate that that checksum is good. If that checksum is bad, by the time, if I sent that packet and you received that packet and the checksum is bad, well, that's not the NIC or, routers corrupting that. That's something at the TCP layer that is corrupting that. So, okay, I got another question. What does it mean when a client sends a sync and the server replies with a reset? Well, that's really pretty simple. Basically what that is saying is if you're the server and I'm the client, I'm saying, hey, collect call from me. Do you accept the charges? And you're saying no. All right, why not? So why are you not accepting the charges? My guess is the application, so think about in that sync request from the client, I'm sending the sync request to port 80. If the web server service is not running on that box, you cannot accept that connection request. So the only valid response is a reset. You're acting receipt of my sync, but you're saying you reject the call. And again, we talked about that in the previous session, so I would encourage you to go back and review those sessions, those previous recorded sessions from yesterday and the day before. So, okay, what does TCP offer? We just covered all that. Hopefully we're going to show that to you in some packets here. And as I said, I'll show you here all of the different descriptions that you may encounter. Some of these you're going to see in your Wireshark. You're going to actually see the fin packet and the sync packet. And then some of these, the state in the netstat table. What is the state of that TCP? I showed you the one there where it was established. You may see sync sent. You may see sync received. Fin wait 1, the client said it is finished. Fin wait 2, servers agreed to terminate that session. Time wait, we're waiting for some pending packets. Time wait is usually because some idiot application developer, and I apologize if you're an application developer out there, but if you are, please terminate the sessions with a fin. Do not send a reset. When you send a reset to close the application, you're not doing a graceful termination, so that causes that TCP session to be hung for 2 times the maximum segment length, and that is typically 2 minutes. Let me repeat that. That is typically 2 minutes that session is hung. So think about your server now that has all these sessions that are hung for 2 minutes. You're causing basically a denial of service attack against your own devices. So if you're a developer, please terminate the sessions with a fin, not a reset. Microsoft, are you listening? Anyway, I'll get off my case there. So again, what is the state of the connection? There are all of the possible states for the different packets that you may see in the netstat table. Again, if you go to your DOS prompt, type in netstat space -an, you'll see what is the state of those different connections. Okay, enough about TCP. That was a lot, and I apologize that we can't even dig into that deeper, but hopefully that's enough to get you started into the TCP process. And I encourage you to continue your learning of that process via reading some books. There's a lot of good books on TCP/IP out there. So we started initially. We're going to jump into Wireshark here, and where this came from is I had a person contact me and say that they were having problems, and the application people were saying it was their network, and they were saying it was the application, and the typical finger pointing thing of where's the problem. And they were experiencing, because of this, they were experiencing some monetary financial loss to their organization. So I helped them out here. We started with the process. I said, let's go time the TCP three-way handshake. So here we go. I've got a relative column. And again, if you've just joined us today and you don't know how to add columns, I would encourage you to go check out my website and go through that process. I've added some columns to my Wireshark that allow me to measure time. So our relative time column, I'm going to time our sync request just so that I know what is the network round trip time. So we see the sync from the client. We see the sync ACK from the server and the ACK from the client. We see that takes 158 microseconds. So, oh my goodness, the network is fast. So there's our network round trip time, 158 microseconds. So I know that anything else, is going to be application, server processing, time related, whatever. I now have the definitive time as what does it take to get from this client PC to this server, and what is our network round trip time, 158 microseconds. So we need to start looking at, what is potentially the problem. Again, in this case, they were complaining that the application was saying it's the network, and the network people were complaining it was the application. So we had to go figure that out. And I'm gonna go to some specific frames because I helped them solve this problem. Now, this was not the exact trace, so unfortunately, I can't give you the exact trace or show you the exact trace, but I can give you a very similar example. I'm going to go to frame 3446 here. And we're going to go through some of those TCP things that we just talked about. And you're going to notice Wireshark says, hey, I got a TCP Act Unseen Segment. So this is where Wireshark is saying, I've got some data here that I don't have the, there's some stuff that's missing in the middle. I've got a packet here that I don't have previous packet information for. So typically what causes those kinds of things are, again, if you missed our previous webinars, when you set up span sessions, switches don't always forward all the packets. They are busy, and especially on, very busy links, those switches are very busy switching packets. They don't, give the priority to sending packets down the span session. So here's one of those cases where we can presume potentially that the switch didn't forward the packet to Wireshark, or that Wireshark was too busy and it, the NIC on Wireshark wasn't able to keep up and process. But one of the two, we need to be able to prove that, and that's what we're going to do here very quickly with the TCP sequence numbers. So a couple things here. We notice ports. We've got our socket circuit session combination there. Port 19813, talking the 51198. That defines our TCP socket circuit session that we established with that sync request. I filtered down to just this one conversation pair. And in this particular frame, we see sequence numbers. The sequence number here And remember, these are big numbers. They're 32-bit numbers. Now, you may have on your Wireshark has an option to use relative sequence numbers where it sort of hides the real sequence number for you. Not a fan of that, but if you are, your choice. You can turn that on or off in your preferences here, screwdriver wrench. If you go to protocols and you go down to TCP, I'll show you where that's at. And again, if you like it, hey, it's your thing. It's your thing. Do what you want to do. I'm not a fan of relative sequence numbers, so I turn them off. But by default, I believe, Wireshark has that turned on, and then it hides, masks the real sequence number. So I turn off relative sequence numbers, and then I get the actual 32-bit sequence number that if you highlight that, it shows you the 4 bytes in the frame, and I can use a calculator and that all works, and I can prove to myself this whole process, and that's exactly what we're going to do right now. So in frame 3446 here, where we're at, we see the sequence number of 793399611. We're sending 1,448 bytes of data, so we said sequence number plus payload length equals the appropriate ACK from the other side. Or in this case, Wireshark is doing the math for us with next sequence number. So sequence number plus 1448 equals the next sequence number. Well, that would be the appropriate ACK as well. So it's saying that it expects an ACK of 793401059. And we can actually then go find that. Well, we should be able to find that. So if I go to the next frame, we would think that would be, the next sequence number or the ACK. But we notice here in our next packet that the sequence number is not 01059, it's 01086. So we've actually gone a little farther. So once again, since this is math, we can figure out what that is. Just bring up my calculator here and put in 1086 minus, so that's our sequence number here, 1086, minus what our expected ACK was in the previous frame or the next sequence number, 1059. And we can see that the server, in this case, .22, sent an additional 27 bytes in between this packet. So we know that based on those sequence numbers. So from frame 3446 to frame 3447, there was an additional 27 bytes sent by the server that we did not capture. And once again, that would be why Wireshark says TCP Act Unseen Segment. So it's saying there's some data missing here. Now, we've talked about if the normal process is I send data, if I don't get the ACK, I'm going to retransmit data. But in this case, there wasn't a retransmission. It just, kept going. We're still ACKing, and we're going to prove that 27 bytes that is missing here that we don't see, that data was ACKed, and we're going to go look at here in just a second. Notice where we're at in frame 3447. Again, we're at sequence number. I'm just going to use the last. I'm not going to repeat all that stuff there. 1086. So we're at sequence number 1086. We're sending 911 bytes of data. So we expect an ACK, or next sequence number, of 1997 from the client if it received all of that data. So remember our ACK number. We expect now 1997. We're going to party like it's 1997. We're going to press F8, take us to the next packet, 3448. And we see the ACK number is 1997. So that's telling us right there that the client has ACKed receipt of those 27 bytes of missing data as well, along with the original 1448 and the next 900 plus bytes. So we know that that data was sent even though the analyzer missed it for whatever reason. And again, we have to presume the reasons we missed that packet were either the switch, was too busy at the time to forward that packet, so it just, dropped it down, didn't send it down the span port, or it did send it down the span port to the Wireshark, but Wireshark was too busy. The NIC on Wireshark and the PC that was hosting Wireshark was too busy to capture the packet. However, we know that it was there and it was ACKed because of those sequence numbers and ACK numbers. So we can presume that all of the data made it across the network because there was no retransmissions there. We just keep seeing unseen segments. So we can presume either the span port is just overloaded or Wireshark is overloaded, but our sequence numbers and ACK numbers give us the true side of that where we can prove that it made it. The client did ACK it. So again, we can presume because of no retransmissions, it did make it. But here's where the problem then started, or how we can sort of prove that there was a problem and what we did then to isolate and start the process to fix it. So if we go to, let's just jump into where we got some retransmissions going on. If we go to 18, we see there's 18.727. All right, I'm in packet 18.727. I see here my sequence number, 41894, and I've got an ACK number, 66594. There's our ACK number. So we're ACKing a receipt of something. Remember this ACK number, or as George Strait says, write that down, 66594. And we're in frame 18.727. We're going to back up to 18.709. And it sent sequence number 65146 plus the data it expects an ACK of 66594. And remember, we got that ACK of 66594 in packet 18.727. So that data was ACKed from the server. Now you notice the server is sending a bunch of data, and occasionally the client's going to ACK, and we did get an ACK in 18.727. And if we go to, let's see here, if we go to packet 718, we see that the server is sending sequence number 76730, but next sequence number, think about the expected ACK here, is 78178, 78178 for packet 718. Wow, that's kind of magic. Numbers are the same. 718, 718 for the ACK number. That's kind of cool. And we're going to see the ACK for that in packet 18730. There's our ACK number of 78178. So we know that data was ACKed. And once again, we can figure out then, based on those ACK numbers and sequence number stuff, how much data was moved across the network just by using our calculator. So if I take my calculator and I take, we were at 78178. So if I take our high-end sequence number, 78178, and I subtract our low ACK there of 66594, 66594, in those packets there, we know that 11,584 bytes of data was sent from the server to the client, and the client has ACKed receipt all of that 11,584 bytes up to this point in time. So we see that ACK number, 78178. So the client has ACKed that. Server should never have to retransmit that data. However, we say the server should never have to retransmit that data. If I set my relative time right here to where that ACK is, and actually if I go back to 709, let's go back to packet 709 where this whole process started, where we started this. Set my relative time on packet 709. And I go find where it gets resent in 18801. Let's get rid of that time reference. So we can see it's the same sequence number in 18801 that we're resending the expected ACK number stuff. It's the same number. And we can see that our time was 714 milliseconds later. So at this point, we're like, why, if it's already ACKed, if the client has already ACKed receipt of this data, why is the server retransmitting this block of data? Again, the client has ACKed it, but it's going to start, and it's even telling us it's resending from 13 to 79. So we're retransmitting data that has already been ACKed. And so I asked the customer, I said, you know, what kind of a server do you have? What's going on? And at that point, he told me, oh, we have this massive, I don't remember what the model of server was. It had like 16 processors in it and many, many gigs of RAM, and it was hosting this application. And I asked him, well, are you having any problems with other things on, other applications on the network? And he said, not really, but occasionally they would get some complaints, but this was the main application that was being hosted off of this server. So I got to thinking about, well, why would the TCP stack retransmit data after it's already received an ACK for it? So I asked him, I said, by chance, have you turned off checksum offloading on your server, or have you checked to see if the checksum offloading process is enabled on this particular server? He went into his NIC properties, and again, I showed this the other day as part of the capturing process, that you want to make sure that checksum offloading is turned off, especially for when you're doing packet captures. So I went into the properties. He went into the properties of his NIC at the time, and when he looked at the different things, now my NIC does not have the checksum offloading thing there except for proxy ARP and NS offload, which I've disabled, but in his he had IPv4 checksum enabled, TCP checksum enabled, and I asked him, turn those two options off, or turn off anything that offloads the checksumming to the NIC, because you've got 16 processors and you've got one little FPGA or some mini processor stuff going on the NIC to take care of all of this checksum stuff that has to happen at TCP. And so he made the change that evening. He turned off the offload engine process on his NIC, and lo and behold, the next day everything was working fine, never had any more problems. And that was the issue, that the NIC just could not keep up with everything that the TCP, all of the packets. So the TCP stack at the NIC level, trying to calculate all this, could not keep up. So that was kind of an issue, and he ended up having to, solve the problem simply by turning off the transmit offload engine on the NIC. So to see and observe that same process that we just kind of walked through in Wireshark, I'll show you very quickly, it's really fast. That's the beauty of Observer, is even taking the trace with Wireshark. And again, I use multiple tools. I use Wireshark, I use Observer, sometimes Sniffer, sometimes Netmon on the server, S&MP tools. So whatever tools you can get out of your toolbox to figure out where the problem is. But as we showed you in Wireshark, our network round trip time, 158 microseconds. So we saw the same thing in Wireshark. We see lots of packets and, the total time, but we do see these retransmissions. So it's told us we saw those retransmissions in Wireshark. And we're seeing retransmissions here, both sides, client side, server side. We're seeing average client response time, average server response time. We talked quickly about zero windows. There is no zero windows being reported for either side. The client side is not reporting any, and server side not reporting any, which would indicate resource issue on either device. And we're seeing lots of retransmissions too fast, meaning that the device is retransmitting the server, because that's the direction of the arrow. The server is retransmitting packets too fast. So in other words, even though the client acts receipt of that data that we saw in Wireshark, the server is still retransmitting it. We see the duration of this particular socket circuit session was 11 minutes, and then actually when it was captured here just recently back in April. So to go through that same process that we did in Wireshark, in Observer, it's really pretty simple. I just right-click, take that trace, go to Connection Dynamics. I see the same process, all that sequence number stuff that we talked about at the beginning, how TCP starts the session, sequence number 400, expected ACK, sequence number +1, 401. We see the ACK, 401. We see the server send the sequence number 052, +1, 053, the appropriate ACK from the client. There's our three-way handshake. We see that takes, here's our relative time or running time for the conversation. So we see that takes roughly 160 microseconds for the three-way handshake to complete. 600 milliseconds later, the server is sending some data, and client acts it. And so again, green, the boxes are green, the math is good. So we started going down to, let's go see if we can find where we have some issues here. Green is good. There's a react. We jumped down to a packet, I want to say it was about 3,400. Yeah, 3,446. So we'll just go down, that's 31, past it the other way. So 3,446, where this process starts, getting closer. And we start seeing some purple there, skipped packets. That's that same thing that Wireshark was saying was segment unseen, TCP segment unseen. So we're seeing skipped packets. So Observer's seeing basically the same thing, notifying us of skipped packets. So we're seeing data. We're seeing the 1,448 bytes that we looked at in Wireshark, sequence number, 9611 plus 1448. We expect an ACK of 01059. That should be the next sequence number. We see the next sequence number is 01086. So again, beyond where it should be. So that's why Observer is saying, hey, we got a skipped packet. There should have been a packet in there, but we don't see a retransmission for that. And we do see the ACK, again, sequence number 1086 plus 911. We expect an ACK of 01997. We see the ACK of 01997. So the client did ACK receipt of the data, even including the skip packet. So it makes this process very easy to see within Observer. I can see follow the process. I don't, it's very graphic in my face, and then the colors even tell me, hey, the purple says I got some skipped data there. What's the cause of the skipped data? Is it did the server actually send it? Are we going to see a retransmission? Did it ACK it? And in this case, it did ACK even the missing data, so we know that the packet was sent. I can then go down, find that retransmission that we looked at as well in Wireshark. That's down in, I get like 18,727, so that's a ways down there. There we go, 18. So now we're seeing some red. Those are retransmissions. 18, I passed it. So that's what we were talking about in Wireshark, that there were some retransmissions. We saw those, and here we see the same retransmissions, except they're highlighted in red from Observer, saying, hey, those were retransmitted. And I kind of showed you the sequence number stuff out of Wireshark, so not really necessary to show that to you again from Observer. Observer just makes interpreting that data much quicker, much faster. It's all color-coded. I've got all the sequence number plus length. It even tells me the packet that was, retransmitted. So here it says this packet 18203 was sent the original time in packet 18098. So I've got some very quick visual clues as to what's going on with this particular socket circuit session at that moment in time. Okay, so I'm going to turn it over for some questions here. Looks like I got lots of them. Oh my goodness. So let's see, what can I answer here? Frames missing from the trace can also indicate asymmetric routing. I agree, no problem there. I've seen that happen most often with dual home devices. I agree. Again, I don't know that everybody's network configuration. Asymmetric routing can cause lots of different things. TTLs obviously are going to be different. So that's a very good point. Very easy to see in frames. If we do have asymmetric routing going on, look at the TTLs. TTL will be different in one direction than the other as far as if I have double-sided captures, which I always encourage you to have double-sided captures. If I see the TTL, leave client side at 128 and arrive server side at whatever, 115, I know that it took 13 hops in that direction, and I capture it from server back to client, and it leaves the server at 128 and it arrives at the client side at 109. I can definitely tell you we got asymmetrical routing going on, so the frames can tell us that. What is happening when you see TCP previous segment lost? Well, that's a good question. That's typically, again, the analyzer is saying that usually that happens at the start of the capture because you started capturing, you don't have all of the TCP information there. The analyzer is basically saying, I don't have that segment. What we're looking for when we see segment lost is, was it retransmitted? Do we see a retransmission of that data? Is there a way to show ACK number or sequence number in the columns? I presume there, whoever asked that question, you're asking that in Wireshark. So the answer is yes, you can actually do a sequence number, right-click it, and say apply as column. And now I've got a column of sequence numbers. And that's going to move it all the way over to the right. So here's our sequence number. You can drag that column anywhere that you want it now in your list. It's going to reorder that. So now I have all my sequence numbers. So the answer to that is yes. You can do that any which way that you want within Wireshark. Sequence numbers ACKs. You can make anything a column. That's the beauty. What made you look at packet 18801 in that large trace? Well, that's kind of where I just started. I just pulled one of them out. I saw that that was where the same sequence number appeared. So I used the sequence number to come up with that's where I started. I just searched for that same sequence number, and it was retransmitted, but yet the time was pretty minimal. So that's, again, looking for sequence numbers. If it's a retransmission, we should see the same sequence number, and that's where I did it. I have a question of, has checksum offloading? Why is checksum offloading on? Well, don't ask me. I'm not the manufacturer of the NIC. Ask Intel or whoever is your NIC manufacturer. By default, most of the time, they turn on checksum offloading. I'm just kind of telling you, yeah, well, that's your choice. Be smart enough to know what your server is doing, your client is doing, and especially with Wireshark, where you're taking the trace, make sure you turn checksum offloading off. So it does cause issues. Wireshark, it tells us things are in error, checksums are bad, and obviously for this particular customer, it caused their application technically to not perform real well and disconnect a bunch of clients. And by the time they contacted me, they were losing lots of money from their site. So checksum offloading, again, not great. How did the checksum offloading cause the problem? Well, again, checksum offloading is the NIC could not keep up with all the TCP processing that has to happen here. Sequence number plus length is the appropriate ACK. So that was the problem. I mean, again, think about it's got to do that for every session. That's really pretty easy if I've only got 10 sessions going between the client and server. But this particular server was hosting millions of sessions, and yeah, that's pretty hard for the NIC to keep up with all that TCP sequence numbering stuff. So that was the problem. And with that, I'm kind of out of time. I'm going to turn it back to Steve. I hope I was able to answer most of your questions, give you a little bit of information about TCP. I'm going to show you, again, how and where I use Wireshark and Observer, Wireshark on the server and on the client if possible, Netmon on the server. If we have access to Gigastore, that's the retrospective network analysis device where we can actually capture all the packets out of the core. I can then go back in time, pull out the data that I'm looking for when there's a complaint. So I try to use all the tools that I have available to me. Again, Wireshark is one of the tools. Observer is one of the tools. Gigastore, SNMP, information, NetFlow, anything that I can get to give me views, insights into what's going on. So with that, Steve, I'm going to turn it back to you.